Continuing section 8.5 on Coulomb's law, we're going to now look at what happens when we don't just have two charges, but when we have three or more charges present. How can we then use Coulomb's law to figure out the electric force acting on a charged object? So here's example 4, 3 charges on a line. Determine the magnitude and direction of the net force on Q1. So taking a look at this, we have Q1, Q2, and Q3, and their charges are written below, right? Q1 is plus 3 microcoulombs, right? Micro, we remember, is 10 to the minus 6. So that's something you want to keep handy. Q2 is negative 4 times 10, or microcoulombs. Q3 is negative 7 microcoulombs. And we have the distances given here, right? Distance from Q2 to Q1 is 0.2 meters. From Q1 to Q3 is 0.15 meters. So we're trying to find the magnitude and direction of the net force on Q1. So that means we're most focused on Q1. That said, there's a lot of different force pairs we can look at here. And that's what we'll be using, is we'll take Coulomb's law and we'll think about it for each of the possible pairings, right? So we could first start with Q1 and Q2. What direction is going to be the force? What kind of force will there be between Q1 and Q2? Will it be attractive or repulsive? Well, these have opposite charges, so it will be attractive, right? That Q2 will feel a force towards Q1, and Q1 will feel a force toward Q2. So that's a great first start, right? But we can do the same thing with Q1 and Q3. So let's take a look. Q1, Q3, we have a positive charge and a negative charge. So what will the type of force be between them? Well, it's once again going to be an attractive force. They're drawn to each other because they are opposite charges. So we could write it out that Q1 is drawn, it feels a force towards Q3. So we could write that as F13. And Q3 feels a force towards Q1. So F3, 1. Now, if we wanted to, just to take this one step further, we could even look at Q2 and Q3. And these are going to exert a force on each other, right? We note that both of these are negative, so they're going to experience a repulsive force, right? Q2 is going to be pushed away, or feel a force, not necessarily move, but feel a force away, F2 due to charge 3, and charge 3 is also going to feel a force pushing away from charge 2. Now, I mentioned that's going above and beyond because here we're focused on Q1. So all that we care about is this realm. What are the forces that Q1 feels? So we need to calculate F12 and F13. So we're going to look at how Q1 and Q2 interact, and then how Q1 and Q3 interact. And we can use Coulomb's law once again to calculate both of these magnitudes of F12 and F13. So let's take a look at that. All right, so F12, we have K Q1 Q2 over R squared. So K remembers that constant times Q1's 3.0 times 10 to the negative 6 coulombs. Q2, the magnitude is just 4 times 10 to the minus 6 coulombs, right? The negative sign disappears because we're taking the absolute value divided by the distance between them, 0.2 meters squared. And that comes out very conveniently to 2.7 newtons. Very simple number. F13, notice before we even do the calculation, charge 3 has a larger amount of charge than charge 2, and it's also a slightly smaller distance. So because it's both a larger charge and it's closer by, it's going to be a larger force. That's what we'd expect anyways. Now we can do the actual calculation and see if our numbers match. If we get something vastly different, it's a sign we might have plugged it in wrong. So plug in our K, our Q1, Q3, this is where our first change, and the distance, 0.15 squared. Remember that square. And sure enough, it comes out to a number that's about 3 times bigger, 8.4 newtons. Now we have these two numbers for F12 and F13. What do we do with them? Do we just add them together, right, to combine them to get the net force? Well, sort of. But because these are vectors, the direction matters. So notice F13 is in the positive x direction. It's already going in the right direction. F12, meanwhile, is in the negative x direction. So if we want to combine these, because they are in opposite directions, and F12 is in the negative x direction, we are going to need to specify that it is in the negative direction. So when we add vectorially F12 and F13, we have to add a negative 2.7 newtons plus positive 8.4 newtons. So the net force is some number in between them, 5.7 newtons, because the two forces are acting against each other. All right, so here's one example of combining a couple of different forces, right, in opposite directions that we'll have to subtract them from each other. What if instead of opposite directions, it's somewhere in between? Well, just take a look at this setup. We won't go through all of the math of it. If we wanted to find the net force on Q1, we would notice that it's drawn towards Q2 because it's positive negative charge. It's also drawn towards Q3 because, again, opposite charges here. Q3 is a pretty simple one because this force is going to be purely in the x direction because it's just straight towards it, F13. Now, if I want to draw it for charge 2, it's going to be, again, just along the line connecting them, F12, but notice this is now not purely in the x direction or the y direction. It's a combination of the two. What do we do when you have a vector that points in two different directions, or a combination of directions? Well, that's where we go back to our triangles and breaking the vector down into x and y components. So that's what's shown here, where we have F12, but then instead of drawing it as being at this angle of 73 degrees, which is kind of a pain to work with, we can say that it has some small amount of it is pointing along the x direction, and that could be calculated with the net magnitude of F12, whatever that comes out to be, times cosine of this angle 73 degrees, right? Noting that we have a right triangle here. So cosine would be the adjacent side over the hypotenuse, and then we multiply the hypotenuse F12 out to get the adjacent side here. So this would be the x component. So F12x is equal to that. Now, this opposite side will then give us the y component, and so that is given, so F12y is given by the magnitude of F12 times sine of 73 degrees. Once we've broken it down into x and y components, then we can focus on just combining all of the x components and all of the y components. So for this particular example, we could find the net force in the x direction is going to be F12x, just the x component of F12, plus all of F13, because F13 is purely in the x direction. Then we could also find Fy of the resultant, and it's only going to come from F12y, because F13 doesn't point in the y direction. And so these Fx and Fy, right, if I color code them with green, they would make up the net x direction, Fx, and the net y direction, Fy, of the overall force F. And if we have the x and y components and we want to get the overall magnitude, what can we do? That's where we use our Pythagorean theorem, right? All these ideas from last semester are coming back to us. Maybe they feel a little rusty, but that's why we're getting the practice in here. So the net overall force is just going to be the square root of Fx squared plus Fy squared. All right, so that's at least the outline of the solution. You'll get to practice that with a couple of examples in the homework, but that should be enough to get you started there to at least illustrate the framework for solving the problem. And if you have more questions, please do ask on that. Let's try one more example, a little more conceptual, a think, pair, share. So the drawing shows 3 point charges arranged in 3 different ways. The charges are plus q, and minus q. Each has the same magnitude with one positive and the other 2 negative. In each of the arrangements, the distance d is the same. Rank the arrangements in descending order, the largest first, according to the magnitude of the net electrostatic force that acts on the positive charge. And one aside, electrostatic force, I've just been shortening to electric force. Electrostatic is technically more correct in that the charges are not moving, which is primarily what we're going to focus on, certainly for this chapter, right? So you can just focus on electric force, electrostatic force, and not worry too much about that. All right, so if we want to rank these largest first, according to the net electric force on the positive charge, first we want to key in where is the positive charge in each of these arrangements, because that's a big factor here, right? So here's the positive charge for arrangement 1, for arrangement 2, positive charge is in the middle, for arrangement 3, the positive charge is in this lower left corner. All right, now that we've figured that out, what are the forces that each of these positive charges experiences? Well, let's just start with the direction. So for arrangement 1, what direction of force will it experience due to this first negative charge? Well, it's going to feel a force to the right. Okay, what about due to the second charge? It's also going to feel a force to the right, but it's going to be smaller because it's further away. So I want you to see if you can figure this out without checking the solution, right? To see if you can choose an answer. If you're not sure, you can guess, but choose an answer before you move on in this video. So go ahead and pause now. All right, do you have your answer ready? I'm hoping so. Okay, so I already set up 1 for us, and we showed that both the forces are going to the right. What about in case 2? Well, in case 2, we have the first negative charge on the left is going to pull the positive charge to the left, so it'll feel a force to the left. The second is going to pull it to the right, so we'll feel a force to the right. So what is the net force on case 2 going to be? It's going to be 0, right? Because these are canceling each other out. This is a great clue because this is the only one where the charges totally cancel out. So 2 must be the least or last because we want to rank it from largest to the lowest. And so that tells us then that it can only be C or E. That allows us to rule out A, B, and D. That's huge. We've narrowed it down from 5 different options to 2. We now have a 50-50 shot of getting the right answer. So if nothing else, just identifying that with number 2 vastly improves your chances of getting this right. All right, with 3, notice it's going to feel a force upward toward the one charge and to the right towards the other. So this is where it gets a little bit tricky. How do we know which one is bigger between 1 and 3? And the key is that in 3, even though they are in different directions, they aren't in opposing directions. They're in totally different directions, but they're both only a distance d away. So both of these forces are larger than the second force in case 1, which is a much smaller amount of force. Now, if you want to show that more mathematically, you can go to Coulomb's law with F is equal to K times Q times Q. They all have the same magnitude Q, all over the distance squared, R squared. And you could put in the distance, where the distance, R, is either going to be D, or it would be equal to 2D. Now, if you put that in to this equation, you'd find that the first force comes out to K q squared all over d squared. But the second force comes out to k q squared all over 4d squared, because the 2 gets squared as well. What does that mean? That means the second force is a quarter of the first force. So the net force is equal to 1.25, 1 plus 1/4, because I'm adding the 2 together, times this k q squared all over d squared. And if you prefer, you can set q and d and k all equal to 1 for this example, just to keep the numbers simple. And it'll work. So if that helps you out, then you can just say, hey, the net force here is going to be 1 for this top one, 0.25 for the second, so the net force is 1.25. For this other case, the magnitude of the forces are both going to come out to k q squared over d squared, or out to 1. Right? So when we combine them, when we get this net force that is the perpendicular of that, we note that we have a force plus a force, and we want to find the net force. So the sum of the forces is going to have to be equal to the square root of one force squared plus the other force squared. Or in other words, the square root of 2 times the force squared, where that force is just this kq squared over d squared. Or we could write that as just the square root of 2 times the force. If you check, the square root of 2, it turns out, is 1.41 times some other stuff, times this k q squared over d squared. I'm sorry I'm getting so low here. But what this means is that arrangement 3 is larger. As mentioned, because the fact that the charges are closer, both of them are closer, they have a much bigger impact because the denominator is squared. So distance is a larger factor than just pure direction. So it is going to be E. 3 is the largest, and then 1, and then 2. So this concludes Coulomb's law, section 18.5. In the next section, we'll take our idea of this electric force one step further to understand the electric field. So stick around, you're going to want to see it.